decided to call fixel-based analysis, and I'll explain what that's about. So just an outline of the talk here, introduce things a little bit, talk about fixel-based analysis and what that actually means, and then how we do the statistics for that kind of analysis, and then finish with a few applications. So there's lots of different, we obviously want to do group comparisons with diffusion MRI data. It's very important. There's different approaches that have been proposed, and that's by no means exhaustive. But the simplest one is a voxel-based analysis of, for example, fractional anisotropy or ADC. Then there's a track-based spatial statistics, TBSS method that Steve Smith has introduced a while back, and that's become very widely used. Gary Zhang also had a track-based analysis framework, which I haven't seen used a great deal, but it's more about mapping values onto tracks, and a more general way of doing that is Derek Jones's PASTA framework. It's almost lunchtime. Anyway. And then you've got network-based statistics type approaches, which rely much more on the tractography and then mapping certain values from the tracks on that, and then doing statistics on the matrices that you get, and all sorts of other stuff. And I think there's overlap with the previous talk as well in terms of how you incorporate that information into much wider analyses. So some of these approaches operate voxel-wise, some approaches operate on tractography, but none of them really allow a voxel-wise fiber-specific analysis of the diffusion data. But we know there's a lot of crossing fibers. Fiber tracks often cross, and we want to know whether one of them is selectively affected in certain pathology, even if we have crossing fibers. So yeah, almost all group comparisons use these tensor-derived metrics, often interpreted as some kind of surrogate marker of white matter integrity, and maybe something a little bit more, specific, like external degeneration or demyelination or something. But we've long known that these measures are heavily confounded by crossing fibers, in particular, partial volume effects. It affects pretty much, outside of the corpus callosum, the entire white matter, I think, in humans has to be considered to be potentially affected by crossing fibers. So, these simple interpretations just don't really hold. Now, this doesn't mean you can't do these analyses and get meaningful comparisons. It's just that when you start interpreting these results and say we have a reduction in white matter integrity, well, I would challenge that particular interpretation. The problem is there's a lack of alternatives, and that means that people keep using these tensor-derived metrics. And for ages, this has been a real headache for me, because I kept telling people, don't use FA. We've got way better things now. You've got spherical deconvolution and all this stuff. It's great. And they go, so how do I then measure anything about the white matter? It's like, I don't know. So it's been really bothering me. But like I said, the main thing is that the interpretation of findings is ambiguous. So another issue as well is if you use these kinds of methods, you might find that the effects that you're interested in are actually masked by the confounds. So you would have got an effect if it had been a single fiber region, but because it's a crossing fiber regions, you don't see it, or something like that. So nowadays we have new analysis methods that do provide measures that are orientation specific, and that's spherical deconvolution, for example, but also CHARMS, the ball and sticks model. These methods do provide you with at least, most of them, an estimate of the density or the partial volume of each fiber component. So at least that's something that's fiber specific and that we can do something with. And they typically correspond to volume fraction. You can start thinking about other kinds of measures that might be fiber specific, but currently I don't think there's anything that I can think of that genuinely ticks that box. It'd be great to have external diameter distributions that are fiber specific, but that's just almost impossible even if in a single fiber voxel. So if you've got any great ideas, please tell me about them. But the question here is, how do we best perform group comparisons of data that are fiber specific? And that's where the fixel-based analysis comes in. So what's the idea? So as the thing that we kind of tend to look at, in my group anyway, is the fiber orientation distribution, which quantifies the amount of white matter as a function of orientation. That's what the FOD tells you. And we're going to relabel that as apparent fiber density. So that fiber density itself is an interesting aspect to look at. So the question then becomes, if I have subjects 1 and 2 here, and I can establish correspondence, spatial correspondence between them, and extract the fiber orientation distribution at corresponding locations, how can I meaningfully compare these two fiber orientations and, for example, in this case, infer that the fiber orientation that is affected is the anterior-posterior one, whilst the others are not affected. So that's what we want to do. So to do this, we've come up with this framework. It's quite involved, so I'll just take you through it. We start off with individual FOD images, and we put them all in a group average template. So that's very standard voxel-based analysis type approach. So the issue here, well, mostly the issue here is about how do you register data that is orientational in nature whilst preserving all the topology that goes along with it. And can we also use this information to derive the alignment? One of the great things about working with fiber orientation distributions is that you can try and optimize the registration such that you guarantee intra-white matter alignment, which you can't do with a T1 image, for example, because you have no contrast inside the white matter. It's all just one mess of stuff. So here we have a way, because you can see boundaries between the different fiber bundles. We might have a contrast mechanism to align much more finely within the white matter than we could with any other modality. But the thing that's kind of also important is the FOD reorientation, so I'll talk about that. When you do registration, you're going to warp your data in some way, some spatial transformation. And here's an example of a warp that you've done where the whole thing's been kind of curved. If you just map the values that you had in each voxel to the target space, and you get something like this, which is obviously you've lost that topology that you had before here, the kind of continuity information. So we need to fix that somehow. And the way we do it is by taking these FODs and then applying some appropriate reorientation and then mapping them back in there. So that process of reorientation needs to be done with a bit of care, because in this example, for example, it's not just a rotation that I'm applying. There's a kind of shear component to the transformation here, which leaves the left-right orientation as is, but modifies the inferior-superior one. So you need to do something a bit more clever to deal with this. And the way we do it, there's another approach that was proposed by Adam Anderson's group as well. Hong was the first author. So what we've come up with is based on a decomposition of the fiber orientation distribution into a dense set of delta functions. So you go lots of directions. For each direction, you have a little delta function that you represent in spherical harmonics. And you represent this as a linear sum of these components. So it's just a straight linear fit with a minimum norm constraint. Then we apply the local affine transformation that we had from the transformation at that point, for the Jacobian matrix of the warp, to the orientations that we had initially. And we get these orientations. We normalize these to have unit amplitude, and then you end up with these kind of new delta functions that have been warped a little bit. And then we use the weights that we estimated here and sum these delta functions with these weights to get this reoriented fiber orientation distribution. And you sum it all up and you end up with your reoriented fiber orientation distribution. So that's a relatively simple and quick way of doing the reorientation in a way that preserves the topology. Then spatial alignment, obviously, we want to do that well. I'm not going to talk too much about this, but we have based our framework on the symmetric diffeomorphic registration framework that is implemented in ANTS, the SYN framework, which was shown to be performed very well in a study by Klein in 2014. So we want a diffeomorphic registration to avoid all the kinds of artifacts and preserve the existence of the inverse transformation. As I said, this worked pretty well. And just to give you some of the details of how that works, we do the reorientation like I mentioned before. Use a multi-level resolution approach, so downsample by a factor of 2 at the first level and then go to full resolution. In practice, I think we have an extra level again these days as well. Interpolation, we just do linear interpolation of the FOD spherical harmonic coefficients. It's a linear basis, so we can do that kind of interpolation. The final interpolation is cubic. And the metric here is something that we want to look at a little bit more closely, but currently we use just a mean squared error between the SH coefficients of the FOD. And if you take a Cartesian Fourier analogy, that's equivalent to the mean squared error on the amplitude itself by Parseval's theorem applied to spherical harmonics. So basically that's minimizing the mean squared error between the fiber orientation distribution amplitudes. And using this approach, this is a group average of, I think, 15 subjects, looking at the singular bundles, corpus callosum, superior longitudinal fasciculus. And you can see that you get pretty good alignment in this group average FOD image. So that works quite well. Hang on, I pressed the button, but I think it's taken a while. There we go. What we can do with this, immediately you can start to do things that sound pretty cool, like tractography on the template. And that actually works remarkably well. We get a lot of the sulci preserved, and you get a lot of anatomy there that is actually quite encouraging to see. And these oculomotor nerves here. Or is that optic tract? I can't remember. So it looks great. The question is, what do you use group average tractography for? Well, I'll show you, because actually it comes in really handy for statistics later on. But the thing that we really want to do is compare these maps of fiber orientation distributions between patients and controls. So here's an example of, I think in this particular slide, there's 15 controls, age-matched with 15 motor neuron disease patients from Queensland. If I flick between them, you can see that there is a kind of consistent difference between the two. And if I take the difference, this is what it looks like. So you get a very clear difference in the corpus callosum mid-body here, in the kind of M1 to M1 connections, and in the cortical spinal tracts bilaterally. But there's also a lot of other stuff here, and it's pretty hard to see what's significant in this comparison. So you have to do statistics to get something out of this. And to do the statistics, so we want to be able to compare these and correct for multiple comparisons and get reasonable results. And the framework we've come up with here is this connectivity-based fixel enhancement. It's based on permutation testing, and we've devised a threshold-free enhancement procedure, which I'll explain in a minute. But before we do that, we go to the question about what is it that we do want to measure in this thing. In the apparent fiber density framework, is really geared towards measuring the kind of capacity of the bundle or fiber bundles to transfer information, and that's kind of related to how many axons you have, kind of by and large. It's not that simple, of course, but grossly, at a gross level, that's kind of what we want to do. The pathology might reduce the fiber density within that bundle, but the bundle itself remains the same size as it was. We might have a atrophy of the bundle, but the density within the bundle remains the same. It's just a smaller extent. So that's a change in fiber cross-section, we call it. And we might have both combined. So both a drop in local density and a smaller extent of the tract. So that's kind of double bad, because the total number of tracts of axons in here is obviously much smaller than it is in either of these two cases. So the measure of fiber density we use is derived from the fiber orientation distribution. So if we look at this fiber, this peak in this fiber orientation distribution, well, that corresponds to signal that comes from these axons. If we get selective degeneration of that set of axons, then we'd expect to see a corresponding loss in that fiber population. So that's why we've labeled it apparent fiber density. And at this point, you may be wondering why we talk about the term fixel. This is why, so it's a population of fibers within a specific voxel. The reason we came up with the word in the first place is because it gets very boring to talk about comparisons between a specific fiber population within a voxel. So now we talk about comparisons between fixels, and it makes conversations much quicker. we originally talked about talking about directions within a voxel, but that meant we had to talk about dixels, and that was a bit awkward, so we didn't. So I talked before about the fact that we could get measures of density, so just the density itself, or the change in cross-sectional area. So if we look at the change in cross-sectional area in particular, that allows us to do fixel-based morphometry. So if we warp everybody to the same template, you get these warp fields here, and we could make comparisons of these warp fields more or less directly. But we want to do them in a fixel-wise manner, so orientationally resolved. So the reason we want to do that is if you consider, what you do for voxel-based morphometry. For example, you have a gray matter voxel in patients. That's the region that maps to in the template, and then the controls. It so happens that region is twice the size. Well, it's twice the size. In white matter, it could be a bit different because you might have axons going left, right here, and left, right here. Yes, this is twice the size, but the number of axons is the same. So the information carrying capacity is identical in both cases. But if I now turn the axons around, that is different. There's twice the number of axons here than there are there. So it's a different question. We want to be able to resolve the change in cross-section along the fiber axis, or perpendicular to it rather. And it turns out it's quite simple to do that. All we have to take is what you'd normally use for to get the change in volumes, the determinant of the Jacobian, and divide by the length, the modulated length of the direction that you're talking about. So if that has, for example, got twice the size, well, if the volume stayed the same, that means that the cross-section must have gone down by half the size. So it's quite simple to do. And you can use that, because it's now directionally specific, you can use that directly as a contrast in the fixel-based analysis framework directly. And then you can also do is take your fiber density and modulate it by the change in cross-sectional area to get the fiber density and cross-section thing, which is about the kind of total number of axons that you actually got in that fiber bundle. So now you have three different contrasts in just this particular application here. Local fiber density, very much, I guess microstructural, but this is very much a local level. Cross-section, which is more morphometric. You can look at atrophy of the tracks rather than the selective degeneration of individual axons within them. And then you can combine these two contrasts to give you something that is sensitive to both and gives you something that is about the total information carrying capacity of the whole bundle as a whole. If you see what I mean. Anyway, so just a quick note about what we do to represent the apparent fiber density as a fixel. So for fiber change in cross-section, we can represent that as a fixel by just looking at the change in cross-section along that direction. Fiber density is a bit different because we have this fiber orientation distribution. We want to turn that into a fixel-wise measure. So the way we do this is we take the fiber orientation distribution and we integrate this distribution over a solid angle that corresponds to that peak. And then we just, that's the size of this. So the integral of this is the fiber density measure that we plug into as the value associated with that fixel, that direction. And that avoids issues to do with the modulation of the amplitude that you get due to fiber dispersion. If you think about it, if you've got a nice narrow peak, it's very concentrated, you get a very high amplitude, but a little bit of dispersion and suddenly that spreads out and the peak amplitude is going to get reduced quite drastically. It's quite easy to show that effect. But importantly, the area under the curve is going to stay the same because it's the same amount of stuff. So this is why nowadays we will reduce, we do the integral over that whole peak and reduce it to that value. And that allows us to avoid a lot of these issues. The next thing we need to do is having got all the subjects in alignment, we need to then establish correspondence between fixels across subjects. And there's quite a lot to do there, but just in broad brush terms, what we use is the fixels in the template space. So you put everything in the template space and you've reduced everything to fixels in that space. And then we, in each subject, look for the closest match in a template within some angular tolerance, and by default that's 30 degrees. We also need to specify a mask, and that's a pixel-wise mask now. So that just basically restricts the analysis to those pixels that you think are sufficiently large, that the signal that you've got from them is sufficient that you can actually make any form of inference. And by default, we just threshold at 0.1. And that just ensures that the comparisons are performed in regions that actually have enough signal. And at that point, we can start looking at t-statistics per pixel. So we've got a measure for each pixel across all subjects, and it's just plugging them into a general GLM framework to just get a t-statistic out of this. And you can plug what you want into the GLM, and it can be a correlation analysis. It can be whatever you want at that point. I'm not really going to talk about exactly how you might do this, but it's a fairly standard framework. And then we need to correct for multiple comparisons, because so far these t-statistics are per pixels, and you've got a lot more pixels than you have voxels. So it's a massive multiple comparison problem. And this is where this connectivity-based fixel enhancement comes in. There we go. So how can we exploit the properties of the diffusion data to help us with statistical inference? The problem one is that if you use a standard voxel-based analysis type approach where you smooth over an isotropic neighborhood, I know there's methods to do better than that these days, but that's kind of the classic way of doing it. It's not really appropriate for white matter because you're not expecting changes to be or to take that kind of form. And the other thing is that these clustering methods don't really extend to kind of a pixel representation of the data. So just to kind of have a look at this, if it's grey matter and you're looking at this point, you do smoothing here, it's kind of reasonable to expect points in the vicinity of that point isotropically to kind of show similar changes. But in white matter, if you look at that point, for example, you really would expect changes to be along the tract potentially rather than across the tract. And we have that information because we have the FODs and we have the tractography. So we can use that. So how do we do this? We obviously bring everything into alignment, and let's look at one particular region in the template here. So this is the group average template. You've got superior longitudinal fasciculus and commiseral fibers from the corpus callosum. If we do whole brain tractography on the group average template and look at a particular voxel here, in fact we look at a particular fixel, which is the anterior posterior direction, and isolate all the tracts that kind of match up with that direction, then you get these tracts coming out. And these tell you something about how you'd expect changes in that fixel to correlate with changes along fixels downstream. And we can provide an estimate of the connectivity between these different fixels. So you get a fixel-to-fixel connectivity estimate. And that information provides an estimate of the kind of correlation structure that you'd expect in your fixel data. So we use the tractography to define a fixel neighborhood. And it's based on the proportion of shared streamlines. There's a lot of ways of getting the tractography to a state where it's actually quite quantitative in terms of the connectivity that you get. We can use exactly that measure to smooth along the tracts using that particular framework, which is quite useful to boost the statistics along the tracts. And then we perform this connectivity-based fixel enhancement, which is basically using a TFCE framework. So I don't know if anybody's familiar with the threshold-free cluster enhancement framework that Steve Smith proposed a while back, but it's basically about boosting the t-values in a particular voxel based on the t-values in the neighborhood of that voxel. So if they're all going to have positive t-values, then that increases the t-value in the particular voxel that you're interested in. Well, that relies on a definition of the neighborhood and the t-values in that neighborhood. So what we do is we do exactly the same thing, but I haven't got the equation here, I'm sorry, I had it in a different presentation. We define the neighborhood based on the connectivity that we've just measured here, and enhance the t-values using a kind of weighted neighborhood defined by that connectivity. So now that you have enhanced t-values, so that you know the t-value at that particular point, for example, if all the changes along here are also positive, then you get enhanced t-value, but you still need to correct for multiple comparisons. And the best way to do that is probably permutation testing. We're going to have distributions of very strange. They're certainly not going to be Gaussian. So the way that works, very briefly, I'm not a massive expert on this particular topic, but we can build a null distribution by getting something like 5,000 repeats, but it could be more than that, where you randomize a group assignment, compute your fixel-wise t-statistics based on that random assignment, compute your enhanced, t-values using the framework that I just talked about, and then you record the maximum enhanced t-value over the entire image. And then off you go, and you do that 5,000 times, and then you get an idea of the distribution of maximum t-values for all your repeats. And then you look at what your t-value was at each voxel, and compare it to the null, and basically your p-value is the area above that. That's just, in a nutshell, I think how permutation testing works. And then we can visualize these results. You get two main options. One is you take the whole brain tractography that we had in the template space, and then we extract just the portions of the streamlines that correspond to significant pixels. That's quite a neat way of displaying it, and then you can color code that whichever way you want. I'll show you that in a second. Or you can just display the significant pixels as vector plots, which again I've got examples of later on. What I would like to kind of mention as well while I'm at it, because it's quite a neat trick. In the TFC, original TFC framework, the method was geared at voxel-wise cluster enhancement on a voxel space. And the neighborhood was defined as those connected voxels. So those that are super threshold and connected to the cluster. In this framework here, the connections is defined by that connectivity matrix. So it's entirely possible to have non-significant voxels or pixels halfway down there, but other significant ones down the track, and yet they provide support to each other. So you can have an interruption in a kind of t values, and yet still have enhancement, which is quite neat. So some applications of that, and I'll show you the results. So this is the results in the motor neuron disease study that I mentioned earlier. Oops, I think I went too fast. Come back. There we go. You have to wait a little bit. My laptop's not very good. I think it'll work eventually if I do that. I'll go and prompt it a little bit. So this is the motor neuron disease data that we had. Come on. There we go. Okay. So it's showing basically the areas that I highlighted before, corpus callosum joining the motor cortices, and then both cortical spinal tracts all the way down. You can see this interruption that I was talking about. You still get enhancement even though you have an interruption in the t-values. And that's color-coded by the t-value as well. So we're basically pulling out exactly what we expected to see in this data. This is an Alzheimer's disease cohort that is the ABLE cohort in Australia. It's 46 patients, 94 controls. This is a whole brain tractography on the template, and we just dropped out all the bits that are not significant. So these are all the significant portions of the tract as identified by this analysis. And you can see a lot of the tracts here have been reported before in the literature in different studies. As far as I understand, this is one of the few studies where you can see pretty much all of these tracts together in one analysis coming out. Mostly left lateralized. Apparently that's a hallmark as well of Alzheimer's. And again, color-coded by enhanced t-value in this case. So that's that one. This is now looking at temporal lobe epilepsy, patients versus controls, and we're looking at, so they've all been realigned to have the seizure onset on the same side. Fiber density, fiber cross-section, so this is the morphological analysis, if you want, and that's the combined analysis. And hopefully these movies will start, I was hoping they'll start synchronously, but obviously that's too much to ask. But you can see that you get more results using the combined analysis You get atrophy here localized to just the temporal lobe, and much more extensive changes in fiber density elsewhere. The changes in the anterior commissure, it's hard to know if that's genuinely just fiber density or atrophy, because it's such a small, narrow structure that it's difficult to get an estimate of the change in cross-sectional area in that particular case. But again, recapitulating a lot of the projections from the temporal lobe out to other parts of the brain. Here's an example. This is an isolated case, I think. Single case versus controls, looking at fiber density cross-section and both of them together for multiple sclerosis. I'm not entirely sure I know what the clinical correlates were for this analysis. Again, looking at frontal lobe epilepsy. So these are different genetic epilepsies now. This is all from the Melbourne lab. One gene, you look at fiber density cross-section, and the two, well, that's mostly changes in fiber density. Here's a different gene variant, and that now looks mostly like atrophy rather than changes in density as such. So you get what looks like complementary information from the two types of analyses. Glaucoma, so that's affecting the optic visual system. You do this exact same analysis, mild glaucoma versus controls, optic tract and optic radiations coming out, and stronger again in the severe cases. And a different type of epilepsy, so childhood absence, again, quite extensive changes. I'm not going to dwell on that too much. Chromatoheterotopia, this is where you get nodules in the lining the ventricles, and you get moderate cases and severe cases showing isolated changes versus more extensive changes. Now this is looking at a cohort of adolescents that were born very preterm, and they're scanned at adolescence, so that's 12, 15 years later, and looking at the pattern of changes here, so we get really quite marked decreases. So these now is color-coded by the effect size, so this is a percentage decrease in apparent fiber density. And you can see that in some cases there's really very marked reduction in the density here, and quite extensive changes in the brain. Now this is looking at neonates that are preterm, but now they're scanned at term equivalent age. Looking at the effect of prematurity, so the gestational age at birth, covariating out the age at scan, and again we see quite extensive changes in the apparent fiber density in quite a wide network of the white matter here. So there we go. So fixel-based analysis, I think, is a promising way of looking at diffusion data. I think we can make analyses actually more sensitive and tract-specific by using these methods for boosting statistical power. We use tractography to boost significance. I think this is one of the uses of tractography that I actually think is quite promising. We can look at effects of morphometric and effects of changes in cross-sectional area separately from microstructural effects, if you consider fiber density to be a microstructural effect. And it's applicable to a wide range of fixel-specific measures. I've mentioned just the ones that we use ourselves, which is apparent fiber density. But you can also look at other voxel-wise measures derived from different models if you want to. There's nothing that stops you from doing that. And it makes what we think are minimal assumptions. We just expect changes to be along the tracts, at least for some of their lengths, so that we have this enhancement along the tracts. And we rely on the tractography to estimate these fixel-fixel correlations. So that's about as far as the assumptions go for that particular framework. And with that, we get some good statistical power using these methods. And with that, I'd like to thank you. And if you have any questions, please fire ahead.